example, yeah, in this paper you can find something about such a mixture of 4 different gases which people try to use instead of SF6. And yeah, what's the point? The point is like that. This is attachment cross-section for different components. This is electronegative, this is electronegative. This is kind of buffer gas. So what people would look at? People look at cross sections which correspond to different electron energy. So each component does its job and certain frequency energy. So for example, nitrogen oxide efficiently attached electrons in the low frequency range. That means it will prevent or it will reduce the intensity of kind of number of avalanche which can start in the gas, right? These cross sections of oxygen and CO2, they overlap in some energy range, but they provide the conditions for efficiently distinguish the avalanches which already developed, and the electrons are in the region of 5 to 10 electrons. So that's the idea, and then it's kind of synergy effect, you know, of each mixture does its own job. This also very efficient thing, because molecular nitrogen is such that it has so many excitation levels that electrons which are colliding with it creates excited states. Okay, maybe it's not really good for stepwise ionization, but electrons anyway lose their energy. They should start from the beginning after the collision to gain the energy in the free path. So that's the logic how people do this, and some results really show that, okay, yeah, you may have some combination, different components of such mixture, and that's what provides the best. 30% of each, and then 10% of oxygen. So that gives the best performance for the negative impulse test. So and then after this testing, after this analysis, the testing is done. Actually, there is a group in Zurich, in how's it called? ETH, Genossische Technische Hochschule, or whatever, Hochschule. They are dealing with these things, and they actually start with very basics, with measuring cross sections, then have molecular dynamic simulations for different type of gases, and then at the end come to the test. Okay, these are the most promising combinations. Let's test this. Otherwise, if you do just test, being blind completely, so it would take forever. So there is some progress in that. Yeah. Vacuum. If you go to the left branch of the Paschen curve, it looks like that's the solution, because then we will have ideal properties, or ideal kind of insulating. There is properties because there is no particles to initiate avalanches. Yeah, vacuum is used actually in vacuum circuit breakers, some technology equipment, X-ray tubes, and so on. It's self-restoring, low loss, no loss, low permittivity, high breakdown trends, no flammable, high price. Yeah, you have to really make it with a high precision, with the advanced technologies and so on, to prevent any leakages and impurities inside and so on. Solid spacers. If you have any spacer inside deep vacuum, it will inject charges, so that's for sure. And electrode conditions, roughness. Roughness, that's the killing thing for vacuum applications. Just comparison here. If you have 1 millibar, the free pass is 400 microns, right? If you have 10⁻⁶ millibar, it's 400 meters. So there is nothing to collide with. It's really seems to be ideal, but it's not. So there is emission, which is called Fowler-Peltheim emission type. We will consider this more for the solid materials when we have some kind of tunneling the interface, material vacuum interface. And then the macroscopic current, which can be measured, look like this. So it's proportional to the field. There is exponential term also the field here, and this is the Hawk function. Yeah, so this is, there is a strong field dependence, what I mean of this current. In most of the cases, what happened, if you have any protrusion on the cathode side, for example, so there is a field enhancement. And if the field is enhanced in some way, so it immediately starts this process, and then you have a current, just, you know, particles which are produced and crossing the gap, providing the current. If you connect, if there is another electrode and you connect the ampere meter, you will see the current, how it flows. It's unavoidable in a way. So you have to really polish the surfaces in such a way that they are not creating any field enhancement, but it's not visible really to a certain level. You may have this industrial level of surface roughness, but still there will be some things. So also when the current produces or concentrated on the tips of the protrusions, the current density is extremely high here. And what happens is just started melting because it's overheating, it's just only close, and then produces small pieces of metallic kind of drops, which also coming to the anode side create local overheating in the contact area. So what happened then, you may see here, this is the cathode surface, it's 100 micron scale. This 100 microns, or maybe this also, so that means that this thing is about few micrometers thick, kind of crack on the surface of whatever. So it injects current, and then the current reaches the opposite side, and the anode side becomes like that. It's just metallic drops which are just deposited. Again, this is microscopic level, but the field is acting anyway. So effect of collected material on the breakdown strands. Okay, you can see here, zinc, aluminium, copper, iron, different curves. It's a length between the rod and plane system. So why the difference? Because the different work functions. The work functions are different, the injection process is different, thermal behavior is also different. Yeah. Here you can see the temperature effect. So 1 and 2, this is for copper, 1 and 2. 1 is room temperature, 2 is quite low actually. I think it's liquid nitrogen or something, copper is liquid nitrogen. So you see the cool down with liquid nitrogen. The difference is quite significant because the injection process is temperature dependent as well. Yeah, what the levels of strengths one can reach with the vacuum insulation, it's quite actually high, up to 200-300 kilovolt per centimeter. The impulse voltage is even higher because there is a need for the discharge to develop due to the statistical variations. Long gaps break mainly due to microparticle initiation, and the breakdown voltage may be just estimated with this empirical formula. So this is the constant, and then you have the kind of breakdown voltage proportional to the square root of the distance between the. It's for very rough estimations. Yeah. Solid interface, I will not talk about this at all, but if you have any spacer or whatever, where you have ceramic or kind of polymer, it will create additional charges, and even surface charging may appear, which distort the conditions in the system. yeah, very briefly about vacuum. So I finished this part. It's a brief overview actually. Gas discharge physics is a separate branch of physics, separate branch of different applications. I mean, it's a long history behind, 150 years or something. So there are books like this. So we just take the parts we touch, the parts which are of interest for our area. So if you have any questions, just use time, for example, tomorrow, and try to put the list of these unclear points. So then we can take it at some occasion, for example, when having this exam consultation, then we can make things clear. For now, I want to focus on this. It's about more or less effect of surface contaminations on the breakdown strength. So examples of this comes to surface discharges. So interfaces, what I mentioned at the design lecture, interfaces, they are killing things for any insulation, and that's the reason why. I will just show this. So surface discharges, when they may happen internally, for example in transformers, in bushings, or external discharges, outdoor installations, indoor installations. It's very common. Everywhere when you have interfaces, you may have issues with that. Can be classified according to the distribution of the electric field in the surface. So example here, very simple thing. Two parallel plates. You have air with certain conductivity, permittivity 1, and then you apply some potential, and then you have the field which is uniformly distributed, right? So, fantastic. Nothing like this happen in practice. If you have a solid spacer, just a piece of silicone rubber, which has high permittivity and with lower conductivity, you just insert it somewhere here in the middle, and it has some special shape like this. So touching the electrode in one point, and here is the full contact. So what will happen? If you calculate the field, you will have it like that. If it goes to low frequency, so at low frequency you will have capacitive resistive field distribution, right? It's defined by these guys. So then the structure of the field look like that. The field lines, the strongest field appear on the surface, right? These are the equipotential lines. The density of lines define the field. Right? That's what you can observe. If you go to higher frequencies, where the things are defined to the capacitive weight, so it looks differently. It's concentrated inside here. But then, if you plot the field along the surface of the spacer, that's what you will get. Oh, sorry, not that one, just along the central one. This is even more complicated because of this one, but if you just take a straight line, what will happen? Just here, like this. Here we have triple junction, right? You have contact point of 3 materials. This one, metallic, in terms of potential, air, and this silicon rubber. So if you just look on the field here, that's what we will observe. High frequency and low frequency on this line. Looks like that. So in the middle of the spacer, not much happening, but on the triple junction, it's a disaster because the field difference is 20 and 160 with 80 maybe. It's almost 10 times, 9 times difference. So when you design these things, insulation, so you have to consider this somehow. So under operating conditions, threshold voltage can be decreased due to initiation of discharge charges, you get the field spacer and the electron. So this could be the initiation point for cribbage discharges, for surface discharges, because the field is high. And then it just propagates like that. Space charge accumulation may happen because there is a solid interface where charges can be attracted. Surface conduction and dependence on humidity comes to play, because surface state is very much about the absorption of moisture and maybe condensation and this kind of things. Yeah. This is another example. We have gas, we have solid piece, and then we have electrodes like that. And then we consider this line. We apply voltage to this one. So you have here the electric field lines. So you see the density is high really. So one triple junction here, another triple junction here. So it's very probable that the charge will develop in this way at some point, some conditions. But there is also another probability that it will go this way, through the gas only. And this is really dependent on the conditions. This is just axial field here. So that means that we don't have any normal components acting here. But if you create the conditions for the normal components, just assigning ground here. So you see the things completely change, because then you have lines going like that, and then you have really strong or high density of potential lines and strong field on the interface. So most probably the discharge will not go this way. It will just be attracted to the surface because of the coupling to the ground side, right? That's what happens. There is a field component which goes normally and then tangentially. So the total field is like that, and that's what creates the path for the cribbage. This capacitive coupling to the ground electrode, so the discharge will just simply propagate along the surface. If you look from the top on this story, so usually it looks like that. You have a channel and then it branches and then just covers the insulin. Yeah, the discharge is actually pressed down to the surface, it's attracted to it because of the capacitive coupling here. So depending on the situations, you may have different conditions. For example here, what will happen? Breakdown voltage as a function of the distance between two electrodes. Between each we have the solid cylinder. Okay? So if it's like that, the larger is the distance, the higher is the breakdown voltage, right? It's logical. The higher, the longer is the insulator, the higher is the breakdown strength. And this is again 50 Hertz, positive lightning, negative lightning. So very logical. But now, if you insert another electrode inside, and this could be the kind of bushing. So when you have a conductor inside, and then you have the flange here. This is the flange. So you move this flange, increasing this distance, and that's what will happen. So it's completely different story, because there is a normal component of the field now created, and you, instead of having the breakdown through air, like here, you initiate actually the cribbage discharge, which is needs much lower voltage to propagate. So that's why for the bushings, this is really a critical situation. One need always consider both tangential and normal components of the field. Yeah, gliding discharges, how they can happen. This is the cable termination, just half of it mirrored. It's a symmetric axis here. So it's a cable termination where we have the stress cone. This is the silicon layer connected to the ground. So typically, this is the conductor here, which is under high potential. So what paths one can expect? Like this. Through the surface. There is no way actually to to have a breakdown through the through gas phase in any other way. So for this one, need to shape this properly and select the distances and so. So that's how people usually use these formulas to evaluate the voltages corresponding to the initiation of gliding discharges. So this is geometrical capacitance, and B usually the constants we just applied for different type of terminations and different type of shapes and so on. It's a lot about empirical things. High voltage technology engineering is a lot about past experiences and how people test this and that, and then it generalized, and you have these empirical formulas which are valid in certain ranges. Yeah, another example here, I already showed this. It's bushing. So you have central conductor, then you have the capacitive elements, is already with the grading, right? It's insulating layers covered with the foils, and then you have the wall, which is grounded, whatever it is, transformer tank or the wall of the lab. Yeah, what happened here? Again, there are two components, normal and tangential, because you have the part which makes it makes the normal component really existing. So, and then, yeah, it's about creepage and it's about the internal strength. Yeah, exactly. That's what I'm talking about. So the selection of the sizes of these layers with the foils should not only be based on the capacitance, but also in consideration of the creepage discharges. So one should avoid internal flashovers between the layers. That's why normally these structures, they are put inside certain enclosure, which is filled either with SF6, for example, or oil, or maybe silicon gel, something. It prevents actually surface creepage. Otherwise, there will be immediately flashovers through the internal interfaces. Yeah. How this looks in practice, eventually you will see this in Ludwika. So this is a kind of critical part, because the sizes of these layers, as I said, they are selected based on the capacitance consideration, but then these sizes here, one should provide proper insulation to prevent the creepages in these regions. And then you have this core, which is placed inside the enclosure. This is transformer bushing, so which is filled with bushing type 525. Nothing is written, but I would guess that this is oil, because this is the expansion tank here on the top. Yep. Yeah, internal and external flashover must be prevented. When it comes to air, it's a lot to discuss. It's a huge kind of number of types of this. Insulators which are used, cap and pin, which I already talked about, just pin insulators supporting the conductor, transformer bushings, post insulators, switchgear, composite insulators of different types and so on. Composite, you remember the difference, right? Between this one and this one. So, what is common when considering the possible flashover path? So if this is the insulator, it's a composite insulator. You see glass reinforced plastic core, then housing, these sheds to increase the creepage distance, but the shortest distance between the energized parts is called arcing distance. That's how the flashover happens. From this to these metallic elements over the air, basically, like that. So this is called arcing distance. This is called creepage distance. Then this is the shortest path along the surface, like that. And then the breakdown happens like this, just following the shape of the insulator. And that's one of the ways how to control actually the performance of the insulators under certain conditions, shaping it. And then puncturing, of course. So one can have a puncture of the insulation body, which quite rarely happens. The air is in the interface much weaker parts of the insulation. Okay. What are the conditions or requirements? Okay. Should withstand high electric strength, should survive an environment with dust, UV, rain, salt, pocket, etc. Should have enough mechanical strength. Should exhibit good surface properties, chemical and physical stability in a sense. Yeah, porcelain insulators, I already talked about that. Will not focus much on that. The advantages basically. Immune to environmental factors. That's the big thing which people still affect the choice of people when for specific applications. If there is really aggressive contaminated area, so this is the choice. Resistance to damage by leakage current and discharges, high compressive strength, strong. Limitations, brittle nature. Yes, if you drop it, it can crack. There are crazy people, especially in the US, this is very popular. Take your gun and try to shot the insulators. They are having fun of that sometimes, after being drunk or whatever, because this is really kind of entertaining. If you really target it, it will explode in small pieces. But not much will happen actually from the performance point of view, because if it's cap and pin, so they are just still there. The shed will explode, but the whole chain will be still alive. So, but I mean, this is the drawback definitely. Possibility of electric puncture, yes, not often but happen. Possibility of cracking and failure thermal effect, yes. If it's exposed to arcing, it creates thermal gradients and then it will crack. Titanium glass insulator, these are with a kind of memory effect after thermal treatment, this glass stays mechanically stressed, and then yeah, that brings kind of advantages. Yeah, compressive press rest over layers. What are the advantages of this type of insulators? Again, resistance to UV and other environmental effect. High electric strength, resistant to electric puncture, good compressive strength. Glass cannot be used in certain application due to mechanical characteristics, yes. When there is a vibration or something, this press-stressed condition may lead to cracking simply. Yeah, leakage current erosion, that's what happens on the surfaces. It creates then conducting passes. Polymeric insulators. Composite structures consist in fiberglass core with mechanical stress and then polymer composite housing for weather shed protection. Typical materials used: EPDM, ethylene propylene and monomer, which provides cracking resistance and resistance to UV radiation, which is important for outdoor applications. Silicone rubbers can be HTV, RTV, high temperature or room temperature vulcanized, strongly hydrophobic. That's a very important property because it repels the moisture from the surface. Ability to recover the hydrophobic property because of the diffusion of what is called low molecular component through the rubber. And then you blend it in different ways. Why I'm talking all about this? Because it comes sooner or later to interface properties. Epoxy insulators, this is special type. Epoxy is not used very much today. Yeah, can be molded in different ways, shaping. So that's the important advantage of this. Yeah, and feeding theory can be embedded in the insulator molding. That's also a good advantage, but yeah, this is the main drawback. There is always need for molding. So you have a mold, you fill them with the epoxy, and then it consists of two parts. When you open it, there is a molding line. And this is the weakest part, because all the things will start there. So that's why epoxy insulators, they are limited to medium voltage. And now it comes to pollutions. So if these things are working outdoor, so you always have external contaminations. What it can be? Yeah, active, which form a conductive layer. That's the important thing. And it can be inert, forming binding layer for conductive pollutions. For example, if the line or whatever equipment operates close to the sea, what the typical contaminants? Salt and salt. Right? If it comes to industrial areas, it's some kind of chemicals which comes from the, depends what type of industry is there. If it's concrete plant, for example, then it's a concrete powder contaminates the insulator's time, and it may look absolutely useless. Some waste products, depending what type of industry it is. Agricultural contaminants, it can be soil, some fertilizers, weed killers, and some burning products. Desert, again, sand and salt. I'm not sure really about salt in this case, but it depends on the location perhaps. Other types, for example, salted roads. That's what very commonly used in winter. If it's done on some highway, and you have the lines close to that, so definitely at the nearest towers you will have contaminants on the salted insulators just coming from the roads. Yeah, birds, that's a crazy thing. There were some actually funny videos on YouTube when the bird just coming through the close to the power line, and the drops, and it comes exactly to the insulator and it creates flash or mass. So that's fun, but it's a probability theory, you know. You never know when the bird comes to that location. Okay, it's a table summarizing different things. So locations, type of pollutants, characteristics, and then area, what to do with that, where it appears, and so on. So I will not stop on this. You can just look on the copies on these slides. Weather. So that's the important thing.